Hi, welcome to AWS Innovate Virtual Conference. My name is Tim. I'm a solutions architect with Amazon Web Services. In this presentation, we will dive into AWS Internet of Things service, understand its mechanics, and go over a simple use case of building a simple internet-connected camera, leveraging not only AWS IoT service, but other AWS services such as Amazon Simple Storage Service, S3, and Amazon Cognito. With access to cheaper hardware, cheaper access to internet data, connectivity, customers are growing their businesses in extraordinary ways and have been doing so for years. Whether it's for optimizing their manufacturing capabilities, building great consumer experiences with devices, or monitoring thousands of sensors on oil rigs, our customers are connecting physical things to the cloud in all industries. For example, healthcare solution providers are improving patients' health by tracking biological data and being able to analyze them in real time using the big data services of AWS. In agriculture, customers like John Deere are using AWS to connect people, technology, and insights to uncover new opportunities that will deliver more production in a sustainable way. In the automotive industry, customers like BMW are improving their driver's experience by collecting data from various sensors in the car, processing that data in AWS to make meaningful improvements to their inboard maps. Another great example is in manufacturing industries, where customers are embracing IoT to optimize their production processes and minimizing the downtime of their machines due to maintenance. By using AWS IoT for their machines' sensor data, combined with big data services like Amazon Kinesis, Amazon Elastic MapReduce, and AWS Machine Learning, they are predicting failures ahead of time and thus plan for preemptive maintenance. The business benefits are huge. Imagine, for example, the pressure in my yogurt filling machine's valve has slightly increased for 2 days straight. Given historical data points, Amazon Machine Learning can tell me that I have 90% chance the machine will fail in 2 weeks. That gives me enough time to plan maintenance on the machine before it breaks. The IoT industry is growing exponentially. Customers aren't connecting thousands of devices anymore, but millions. It started with computers, but now more and more things are being connected. From aircon units and thermostats in the home automation field to road signals and building lighting in cities to really precise and time-critical sensors in mining equipment. Industry specialists and consulting firms estimate that by 2020, 1 billion devices will be connected to the internet, 1 trillion by 2035. In connecting millions of things, tracking data from sensors or controlling devices remotely, our customers have been telling us about their pain points. For example, security. How do you secure the communication from your devices and make sure that only your devices can interact with your business logic? How do you deal with the complexities of scaling infrastructure and applications for millions of devices, sometimes designed around custom protocols? And things require hardware, internet-connected hardware. How do you deal with connecting this hardware reliably with the cloud? By listening to our customers, we introduced AWS IoT at re:Invent in 2015. The goal? Simple: to securely connect 1 or 1 billion devices to AWS so they can interact with applications and other devices. We are leveraging a long-running experience of designing and running applications at massive scale and have applied it very securely to the Internet of Things. Now, thanks to AWS IoT, anyone can connect devices to the cloud. Our customers can do so securely, and we've made it not only simple to use, but very easy to get started. So how does AWS IoT work? AWS IoT is centered around the device gateway. This is the centerpiece of the system and where devices connect to. In order to give our customers flexibility and great reliability, we've designed the device gateway to currently support 3 protocols: Mqtt, HTTPS, and WebSockets. Mqtt is an open standard protocol, not AWS specific. Customers have been using Mqtt already by implementing it themselves and creating gateways that support the protocol for a while now. It's a great protocol, very efficient by having a very low footprint for low-powered devices. It's a lightweight transport protocol that supports publish and subscribe mechanisms, enabling live communication to devices. It is estimated that it has greater performance over HTTPS by being 93 times faster in throughput whilst being extremely efficient on power consumption, about 170 times less battery required to receive data. HTTPS and WebSockets are also great because enable other devices to leverage AWS IoT in cases where using Mqtt may be difficult. We have customers using HTTPS to connect their devices to AWS IoT in manufacturing contexts where built-in processes and IT cannot support Mqtt. WebSockets is also amazing. Highly secure, it's a great functionality that allows our customers to leverage WebSocket technology to build web applications, to dashboard incoming data from their devices, and control others. Some of our customers are also using AWS IoT's WebSocket capabilities simply for their websites, and not at all using it for connecting things. Functionally, what does this mean for my app? All communication on AWS IoT is done on topics. Customers can create whatever names they want for their topics, with just a couple reserved topics used for the device shadow functionality of AWS IoT that I'll cover later. In the following example, devices are named 1, 2, 3, and so on. They all report their data to AWS IoT by publishing to my devices / their name topic. From there, we can transfer this data to other services and databases using the rule engine that we will also cover later. Applications and devices can subscribe to a wildcard topic, my devices / hash, in order to get all data that comes from all of the devices publishing to my devices / something. If you want to dive into a specific device, you can also have your application subscribe to that device's specific topic. In this example, our application subscribes to my devices / 4. All data being published to that topic, my devices / 4, will then be received to that subscribed application. Very efficient for tracking the behavior of a specific device, or also for having one device listen and subscribe to events coming from another device. Imagine, you could have a thermometer in one corner of a room or building publishing ambient room temperature to say building name / level 6 / room Y / temperature. Your aircon unit could be configured to subscribe to that topic building name / level 6 / room Y / temperature because you decided to mount it in the same room. The aircon would receive these updates from the temperature sensor via the shared topic, and you could then decide via business logic to have the aircon automatically compensate that increase in temperature. Which brings me to the next example. Devices don't just have to publish information, they can also subscribe to topics. This allows our applications or other devices to make meaningful business decisions around this incoming data. Same as before, we can publish to a specific chosen topic for a unique device. Or we can choose to blast this information out to all the devices connected to the to-all topic. This is quite useful. For example, you could use this method for firmware updates of a fleet of devices. Or simply, in the case of WebSockets, imagine if that topic was a room in a chat application. Writing to that topic would notify all subscribed users of that room. We support two quality of services levels for Mqtt, QoS 0 and 1. When configuring QoS to 0, at most once, you publish in a fire and forget mode with TCP guarantees. This means a message will be delivered 0 or more times. Quite useful in applications where it is okay to lose one data point, because your applications are aggregating the data and applying filters, for example. Here, data points at given times are published to AWS IoT. Messages 1, 2, and 3 are instantly received. But let's say at the time of sending 4, there's a communication issue. That message is then lost. It doesn't matter. My temperature sensor is sending data twice every hour. Worst case, my application logic will receive the next data point after 1 hour. Not very critical to my previous temperature and aircon example. In some cases, however, data is critical and you want assurance that your message was properly received. That's the quality of service level 1. It is guaranteed that a message will be delivered at least once to the receiver. every message is acknowledged at the application layer. Very effective in business-critical phases or when you cannot miss one data point or sequence of data points. This does have some extra cost involved because you are doubling the amount of requests. Let's come back to AWS IoT. We have our device gateway, but need to connect to it. We provide device SDKs for a variety of platforms that greatly simplify connecting your devices to AWS IoT. That connection is secured with mutual authentication using X509 certificates and TLS 1.2 encryption. With AWS IoT, AWS currently provides 4 SDKs. The Arduino Yun SDK that integrates with the Arduino IDE, its libraries, and the whole Arduino hardware ecosystem. The Node.js SDK, which allows connecting all Linux-based devices to AWS IoT. For example, from really cheap $9 Linux devices such as the NextThing chip, the Intel Edison boards, or Raspberry Pis that we will be using in our demo. You can even integrate it in your Linux servers to leverage publish and subscribe capabilities of AWS IoT. The Embedded C SDK, that is great for strict hardware constraints that require to run on microcontrollers, for example like Microchip, Texas Instruments, or MediaTek devices. And finally, the mobile SDKs for Android and iOS. The SDKs are great because they provide the high-level libraries that enable you to focus on your business logic. Connection to AWS IoT is managed by the SDK and includes the strong security authentication and encryption. On the subject of security, AWS IoT is centered around 2 pillars. Authentication. This guarantees that only that specific device is connecting to AWS IoT. This is under your control. You can use AWS IoT to generate X509 certificates, or you can bring your own. If you want to retire a device for security reasons, you can simply disable its certificate from the AWS IoT side, and that device will not be able to connect anymore. Encryption. This guarantees that the data you are communicating to and from your devices is encrypted. It is end-to-end encryption. No eavesdropping, no tampering becomes possible. Now that our devices are connecting to AWS IoT, the question is, what becomes of the incoming data? How do we integrate it with our backend infrastructure? We built the rules engine into AWS IoT, which allows to integrate with other AWS services like AWS Lambda or event-driven calculations, or storage directly into Amazon DynamoDB or Amazon S3. The AWS IoT rules engine is a simple SQL-based query that you attach to a given topic. All data flowing through the specified topic will be queried by the rule, and if the query returns something, the rule-specified action will be triggered. For example, if my rule is select star from things/thing2/color, where color equals red, then all data flowing through the things*thing2/color topic will be picked up by the rule. If the data has a color value other than red, nothing will happen. In the case of red, the rule will trigger its specified actions. Depending on your use case, rules can be defined to being very specific, only this very specific data point from this very specific device, or you can wildcard your topics and not specify any specific where clause, meaning you may want to trigger the rule on all data, whatever that data is, coming from all your sensors. AWS IoT Rules Engine actions are triggered on matching queried data. You can choose from many actions, and you can run one or many actions on the trigger. You can invoke a Lambda function. When the rule picks up data from the topic, the data is forwarded to a Lambda function that will do whatever complex calculations you want on the data before forwarding it on to other services or storing it into your databases. You can store the data directly in S3 for archiving or buffering it for later use. Or why not inserting it directly into a specific DynamoDB table of your choice? You can republish to other topics or connect to Amazon Kinesis Streams and Firehose, or Amazon Elasticsearch for deep querying and dashboarding using the built-in Kibana. You can forward the data on to simple notification service that will enable you to integrate directly with mobile push notification services or send emails and SMS. Imagine, I've installed a proximity sensor in my home. It detects movement while I'm at work. Instantly, I can receive an SMS or push notification telling me there was some movement. Good thing I've built an internet-connected camera. I can automatically have my camera trigger taking a picture of my front door for me to look at. Oh, that was close. Only my dog entering through the dog flap. Now that I'm triggering actions on my incoming data, what I'd like to manage is the state of my devices and have my applications interact with that state even when my devices are offline. Thanks to the AWS IoT device shadow functionality, I can do that. AWS IoT holds a virtual representation of your device in the cloud. It holds the state of parameters you choose to synchronize, allowing your applications to interact with the state device. Reading it, changing it, without the device necessarily having to be online at that specific moment. Your applications can read the last known state that the device reported and request that the device change its state to something else. AWS IoT manages the delta between your reported and desired state for you and synchronizes with the device when it is back online. Your device can report its state. For example, my engine is on, my light is green. My application sets the desired state. Here, engine should be on and light should be red. The AWS IoT device shadow functionality automatically calculates the delta, in this case, light should be red, and publishes this directly to the device. Up to your device logic to not only change the light color, but also report this information back to AWS IoT to clear the delta. For example, let's assume I've just bought an awesome new car that I can remotely control with my car's mobile application. At a given point in time, the last reported state of the car is that its engine is off and that the speedometer HUD display is configured to green backlighting. Yes, my new car is so cool that I can choose to configure the inboard dashboard to different colors. Now, of course the car's engine is off because yesterday I parked it in my driveway and it's been sitting there all night. Periodically, or last time I turned it off, that's what the car reported to AWS IoT. Now, I've just woken up and I look out the window. Oh dear, it snowed and the car is all covered in snow. I can pull out my mobile app and tell the car to turn its engine on to preheat it, for example. My mobile app will write to my car's device shadow that the desired state for the engine should be on. Automatically, the device shadow constructs the delta. In this case, there's a mismatch between the desired and the reported state of the engine, so the delta is engine on. My car receives this delta from the device shadow, notifying it that the engine is desired on. The car should turn on its engine and report the new state to its device shadow. This will have the effect of clearing the delta state of the shadow. Report and desired state are now in sync. I can go have a quick coffee and off to work. Hopefully, the engine will have melted the snow by then. We've covered the device SDKs, security, the different protocols, the rules engine, and the device shadow. Finally, AWS IoT, like all the other AWS services, has an API that integrates with our full AWS SDKs, but also the AWS CLI, allowing you to programmatically create new things in AWS IoT, manage their certificates, their policies for security, as well as query and tag your things, thanks to the device registry that is built for managing your devices. From one device to the millions that you need to monitor and track. We have a growing list of partners that provide development kits centered around their hardware devices that allow customers to get up and going using AWS IoT in a matter of minutes. Each of the development kits that you can get from hardware distributors or even Amazon.com integrate the AWS IoT SDKs, allowing you to focus on your business logic and value rather than on connecting your devices to the cloud. Partners like Broadcom, Marvell, Microchip, Intel, or MediaTek. All of our partners provide their kits to enable you to use their specific hardware chips, like the Intel Edison that operate around a Linux distribution that allows you to integrate the AWS Node.js IoT SDK seamlessly, or MediaTek with the C SDK leveraging Arduino IDE. These are great kits to get started. You don't have to use those kits specifically. There are numerous other options available. Most Linux boards are compatible with AWS IoT, as well as a lot of other microcontrollers. you will very easily find hardware chips that will allow you to leverage AWS IoT and design your business logic around it. We have an increasing number of customers that are using AWS IoT for so many different use cases. For example, Sonos, who designs great home equipment, has managed to leverage the value of AWS IoT in their existing hardware designs without having to redesign. They discovered, and to quote them, that a 10-year-old product can do things that hadn't been invented 10 years ago. Most importantly, going forward, people will expect your product to improve, and if it isn't being updated and getting better, you're literally being left behind. By integrating with AWS IoT, Sonos analyzed mountains of usage and telemetry data from their devices in the field to make sure that their products operated as per their standards for their customers. Their TruePlay technology measures the acoustics in any room and fine-tunes your speakers for a great customer experience. They launched these updates in 2015 using AWS IoT on devices that their customers purchased over 5 years before that, simply with a firmware update. A great case of building new with the old and improving customer experience centered around innovation, data-driven evaluation, and testing. Ratio is also a great example. Ratio designs and develops easy-to-use smart irrigation systems that can be controlled remotely from a smartphone in the cloud. It provides water usage reports, a history of timed and manual watering, and numerous alerts and notifications to train the user on better watering practices. Better yet, it uses your local weather data to automatically adjust your watering schedule to help conserve water. The Ratio team approached us with a simple need of wanting to focus on their business. We want to make great sprinkler controllers and save water, not manage an IoT infrastructure. By leveraging AWS IoT, Ratio was able to do just that and save 40% of their development cost. By integrating their controllers with AWS IoT and a lot of other services like Elasticsearch, Elastic Beanstalk, Lambda, and more, Ratio managed to focus their efforts on their customer experience rather than have to deal with building and managing a scalable, secure, and highly available IoT infrastructure. These are just two great use cases of leveraging AWS IoT. As a second part of this presentation, I want to show you how easy it is to get set up running AWS IoT. Let's build that internet-connected camera I talked to you about before. What you'll need. I'll be using a Raspberry Pi because it has a simple camera module you can connect and use. And there's a great amount of documentation available online for using the camera. I'll assume you've already got the Raspberry Pi set up and ready to go with Node.js, because we'll be using the AWS Node.js IoT SDK. We'll be using just a couple AWS services for this demo, AWS IoT obviously, but also Amazon Cognito and Amazon S3. Finally, all you'll need is your computer, motivation, and a couple lines of code. Let's dive in. This is our connected cameras architecture. On the left is my Raspberry Pi and camera module. I'll be using Amazon S3 and AWS IoT. On the right is my phone or computer. On the Raspberry Pi, our Node.js code using the AWS IoT SDK will connect to AWS IoT and subscribe to the camera/button topic. Easy as that. We'll be using S3 for two things. First, we are using S3 to host a static web page. S3 has a great feature that allows you to host websites in your bucket. Simply upload your website code to your S3 bucket, configure the bucket for static web hosting, and voila. You now have a great web hosting for really cheap and no need for a web server to run in the background. Second, we will use S3 to store the uploaded pictures that my camera will be taking. So we load our HTML and JavaScript web app onto our browser. The web client JavaScript code loads the AWS JavaScript SDK and uses Amazon Cognito to obtain an IAM role, giving it permission to connect to AWS IoT and subscribe to another topic, camera/uploaded. At this point, my devices are connected and ready to go. On my web page, I've placed a button. Pressing that button will publish a message to the camera/button topic. Here, I'm using the web pages for simplicity, but if I reuse my previous example, I could have any other IoT device or business logic published to that topic. My proximity sensor detects movement. It publishes to the camera/button topic. The sensor could publish Or you could manage this from the rules engine. Say my proximity sensor was publishing its proximity data information to AWS IoT. That's all the sensor does. I can design a rule on the incoming data from the sensor and republish to another topic, sensor/proximity sensor/data. I can add a where clause to trigger only if the proximity sensor value exceeds a certain threshold, and as an action, republish this data to the camera/button topic. Basically, my proximity sensor could publish its setting data readings to AWS IoT, and the rule engine would send this data across to my camera if the value exceeds a threshold. So, my Raspberry Pi who subscribed to the camera/button topic receives the event. My code picks up on the event. It uses the camera module to take a picture. For simplicity, we will use a UTC timestamp for the file name. Once the picture is taken, the Raspberry Pi uploads the picture to S3 in a predefined S3 bucket folder using the AWS JavaScript SDK. Then, my Raspberry Pi publishes to another IoT topic, camera/uploaded, in order to notify all subscribed devices and applications that a new picture has been uploaded to S3. In my previous example, this is where I could design a rule that waits for messages to trigger on camera/uploaded, and I could pass this on to the simple notification service to send me a mobile push notification so that I can view the picture in real time on my mobile app. Or a great fun thing you can do, you can invoke a Lambda function every time camera/uploaded is triggered. In your Lambda function, you could very simply integrate the Twitter SDK and post your images to a Twitter feed every time the camera takes a picture. The whole world can know that your dog Pongo just entered through the dog flap. In this demo, I'm keeping it simple. No Twitter, no mobile app. Publishing to camera/uploaded only gets picked up by my website. Since I'm publishing the file name to camera/uploaded, my subscribed website can display the image live from S3 using the file name in the message. Here's the result. Haha, there's my dog Pongo wearing his party glasses while posing next to the plant. This is a screenshot of the website for this presentation, but hang on, we will run through the demo live. Now that we've gone over the architecture, let's build this demo. First steps, let's get the minimum credentials and security in place. My Raspberry Pi needs to upload pictures to S3. Uploading images to S3 will require that I use access keys. I should use Cognito for this, but for this example, I've chosen to use user access keys just to show you this option and leverage the device shadow to pass on these keys to the device. In Identity Access Management, we will create a new user, and we will make sure to restrict the access of that user to only accessing our specific S3 bucket. This is achieved by attaching the shown policy on the right to that user. The user only has access to uploading and viewing files from a very specific S3 bucket. Note that it could be argued that using an IAM user is not ideal here, because this would be having to use an API key and secret in your device. In some cases, however, you may need to connect to AWS IoT using the HTTPS RESTful API, and you will need those keys for that. Not only is it critical to secure the access of those keys by enforcing a very strict IAM policy on that user, but for our demo, I'm making sure they are never stored on the device. The device shadow on synchronization will pass the keys to the code. I'm inherently using the authentication capabilities of AWS IoT via the device certificate to get the access keys from the device shadow that will allow the camera to upload to S3. For our website, we will be using Cognito to authenticate to AWS services. We create a Cognito identity pool for which we allow unauthenticated access. Cognito could also allow us to use social logins such as Facebook, Twitter, etc. to authenticate and access AWS. However, for the purpose of this demo, it's not necessary. The access we are granted by Cognito can be restricted with a role. In our case, we restrict the access to the bare minimum. Our user can only connect, publish, and subscribe to AWS IoT, period. Now that we have the IAM roles and policies in place, we need to create our thing in AWS IoT, create a unique certificate for it, and finally give it a policy that will restrict the actions that it can do. I've called my thing Pi Camera. I'll create the policy you can see that allows my Pi camera to connect, publish only to the camera/uploaded topic and subscribe and receive messages only from camera/button topic. No need to give my camera more access than it needs. This way, not only is this a very simple demo, but it's also very secure. Now it's time to code. This shows the strict minimum code that I'll need to run on my Raspberry Pi, configure the AWS IoT SDK and connect to it, and implement the minimum callbacks. On connect, I register my Pi camera to its shadow, and I subscribe to the camera/button topic. On message, this is where I receive data if someone publishes to my subscribed topic camera/button. In that callback, I need to take the picture, upload it to S3, and then simply I just publish to the camera/uploaded topic with the picture information. On Delta, this is where I receive Delta information regarding the state, and in my demo, I'll be receiving the access keys to use to upload files to S3. Once your code is ready, you can simply test it. AWS IoT's Management Console has an Mqtt client that you can use to connect. You can subscribe to topics and view the incoming data, as well as publish to topics. In this screenshot example, I've published a camera/button, the object event from Mqtt client. And I've subscribed to camera/uploaded to see what my camera was doing. Here, you can see I received a message on that topic, giving me the file name it uploaded, as well as some extra information I've built into my demo, like the tweet text, in case I want to also implement the Lambda post to Twitter functionality. So at this point, it's great. My camera is operational. If I publish on camera/button, my camera takes the picture, uploads it to S3, and publishes on camera/uploaded. Awesome. Now this is the last part. I need to build a simple static web page that leverages AWS IoT WebSocket protocol to subscribe to the camera/uploaded topic and publishes to camera/button with a simple button on the page. You can find Getting Started sample code on the AWS Labs GitHub repository, as well as documentation on how to connect to AWS IoT WebSockets in the official IoT documentation on the AWS website. Let's switch over to the demo. I've pre-recorded it for the purpose of this presentation. Before we look at the code, let's get set up on the AWS Management Console. Let's go to IAM and set up our Camera Pi user. I've already created the user, and we can see the access key here, starting with AKIA. I will later be passing on this access key and its secret to this device, Shadow, for my camera. Let's look at the permissions I've given to that user. I've created the inline policy named Only Camera Bucket Policy for the Camera Pi user, and here is its content. You can see I've only given it read and upload access to my S3 bucket. With my access keys written down, let's go have a look at the Cognito role that we have created for our website. Cognito AWS IoT Camera Demo Unauth role is the name I gave the role upon creation for the Cognito identity pool. Very simple. I've given it a strict inline policy allowing it to connect, publish, receive, and subscribe to AWS IoT. Let's head over to Cognito to have a look at how that's set up. Here, also, I've already prepared Cognito Identity Pool, AWS IoT Camera Demo. We can view its identity pool ID in the sample code section. My ID is AP Northeast 1 409C2, etc. Let's have a look at the configuration details. I've enabled unauthenticated access and attached the Cognito AWS IoT Camera Demo Unauth role. Even though an authenticated role has been created for it, I have not enabled any authentication providers. Now that I've created the accesses for my different application, let's head over to S3 to have a look at my website. In the bucket I've created, a typical HTML and JavaScript web application. I've configured the bucket to enable website hosting and pointed the index.html document to my web application's index file. If I drill down into the images folder, you can see the growing list of pictures my camera has been uploading. Now, let's go have a look at the AWS IoT configuration. I've pre-created a thing its policy, and certificate. My thing is Pi camera. We can see the shadow object for my thing, containing in the desired section the access key ID and secret access key, as well as the other configuration parameters I've added. We can also see its linked certificate. I've already downloaded the certificate on creation, and I've copied it into my Raspberry Pi. Both the Pi camera thing and the Pi camera policy are attached to the certificate. If we view the policy, we can see the strict constraints I've given it. The camera will only be able to connect, subscribe, publish, and receive to the specific camera/button and camera/uploaded topics by using the specific ARNs. We're good to go. Let's have a look at my Raspberry Pi code. I'm loading the AWS SDK for S3, as well as the AWS IoT Device SDK. I'm using the Camera Pi module to access the camera. I've stored the endpoints and bucket names in a config file, and I'll be referencing them throughout the code. You can see my IoT config, where I'll be loading the certificate and the private key, as well as my account's AWS IoT endpoint. I initialize my state to null values, and this is where I initiate the connection to AWS IoT with the IoT configuration. I've implemented the minimum connect, delta, and message callbacks, as well as the close and reconnect just in case. On connect, this is where I'll register to my camera's device shadow, as well as subscribe to the camera/button topic. On delta, this is where I update my local state. You can see here that this is where I'm receiving new access key and secret from the device shadow. On message is when I receive messages on the camera/button topic. I start by taking a picture via the camera module, and then upload it to S3, using the credentials from my state object. On successful upload to S3, I finish off by publishing to my camera/uploaded topic, the file name for my website to use. We're ready to go. Let's run the demo. We'll use the Mqtt client to view what is going on. In the Mqtt client, let's start by connecting to AWS IoT with a random client ID. Then I need to subscribe to the camera/uploaded topic. This will allow me to view the incoming data from my Raspberry Pi. Now, I'm going to simulate pressing the button by publishing a random message to camera/button. Let's write the message, click from Mqtt client to camera/button. In my example, it doesn't really matter what I'm sending. My Raspberry Pi should trigger a picture and upload it to S3. Let's wait for it. There it is. The Raspberry Pi has reported the file name, the picture it uploaded to S3. Let's switch to my S3 website. Let's refresh it. In the web console, you can see that we are connecting via Cognito and receiving temporary credentials to connect to AWS IoT WebSockets. Let's press the button to publish to camera/button. Let's wait a couple seconds, and voila, a live picture of me next to Pongo. This concludes the demo. We now have a fully functional internet-connected camera. To gain more confidence and hands-on experience with AWS, watch our instructional videos and explore the self-paced labs. Attend our instructor-led classes by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. Validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. I hope you found this deep dive on AWS IoT as well as this demo building exercise useful. Do provide us with your feedback and let us know how we can improve the event experience for you in the future. And remember that SAs like myself are here to help you architect your solutions on AWS, so don't hesitate. Thank you for your time and hope you enjoy the rest of AWS Innovate.